something that I want to start this lecture off with this thing about different types of methods for solving optimal control problems. We're not going to go into all the details at this point, but I want to do a little bit because I think it's important that when each of you is looking at the problems on the homework and thinking about what kind of problem you want to do for a project, that you get some sort of an introduction to the computational aspect of optimal control. Because fundamentally, optimal control problems cannot be solved analytically. You know, this is really great if we could write analytic solutions for everything, but that's just not reality. So one of the things that I like to do when I'm teaching like a survey course on optimal control, like not in an academic setting, but more in an industry setting, is lay out this concept of what it means, what's required to actually solve optimal control problems. So today what I'm going to do is I'm just going to give you a very bit of introduction to numerical methods in optimal control, and I'm going to focus on what are called indirect methods. So, and then later on in the course, I'm going to do a lot more with direct methods. So we'll talk about that later. But right now, I just want to this is just sort of an introduction to computational optimal control. And I'm not, like I said, it's not comprehensive, but it's just a bit to get you started. Now, optimal control. So I'll start with this statement that virtually all optimal control problems must be solved numerically. Because analytic solutions do not exist. Now, when we think about how we're going to actually solve optimal control problems numerically, we have to decide the class of problems that we're going to use, the class of methods that we're going to use to solve these problems. Now, if you remember, when in the very first lecture I did in this class, we talked about a function and minimization or maximization of a function. And if you remember, I said that if you want to minimize a function f of x, I'm just going on a slight aside here, just so that we can get sort of the context of all this straight. You remember that one of the things was if f of x was smooth and it was differentiable and we didn't have any constraints on the domain or anything like that, and this is a scalar function, that if we compute df dx and we set it equal to 0, and then we find the critical points, those critical points will tell us, if we then check the second derivative at each of the critical points, we want to see whether or not they're greater than 0, and that gives us a local minimum. And then the same thing is true if d second f dx second is less than 0, then that's a local maximum. And if the second derivative is equal to 0, it's an inflection point, right? Now you remember, I didn't talk about this then, but if you look at this problem of finding the critical points, let's just focus on that for a second. So finding critical points of functions means that we're going to set this derivative to 0. Well, what kind of a problem is that when I say I'm going to say df dx is equal to 0? It's an algebraic problem, right? What kind of algebraic problem is it? You all know it. When I say it to you, you'll say, oh, yeah, it's that kind of algebraic problem. It's a problem of determining roots of a function, right? So this is a root finding problem. Now look what you're doing here. This is root finding. Because I want to find the roots of that function, df dx. Now, when you say you're going to find the roots, am I doing any optimization here? Am I doing any minimization or maximization in the process of solving this root finding problem? No, I'm not, am I? This problem is an algebraic problem that has nothing to do with optimization whatsoever. It has to do with determining the zeros of a function, right? So that those zeros of the function, but in the end, I'm interested in optimization, right? I'm interested in minimizing or finding minimum or maximum of a function. So this approach, even though you've never heard it referred to this way, this is what's called an indirect method. It's indirect because you're not actually minimizing the function. You're finding the condition that would lead to possible minima, and then you're algebraically trying to solve that particular condition. It's a necessary condition, right? It's not a sufficient condition, because you don't know until you check the second derivative whether or not it's a minimum or a maximum. This is classically known as an indirect method. Nobody who ever introduces the subject of functional, of like function minimization, and then, in calculus when you talk about derivatives, ever talks about this as being an indirect method. But it is an indirect method. So that's the first category of ways that you actually solve optimization problems, is this thing called indirect methods. The second category is not that at all. The second category is what's called the direct method. In a direct method, you never actually try to solve this particular problem. What you do is you work on this problem directly. You say, all right, I have a function. I want to make it as small as possible. What's the value that makes it as small as possible? Well, you can think of the really naive way of doing this is take a guess and plug it in, right? And then you can say take another guess and plug it in, and just keep taking lots of guesses and plug it in. And then, if you've plugged in every single value that you possibly could, the one that gives you the lowest value is the one that minimizes the function. That's clearly not a very good way to do this, right? But it's a direct method because you're directly trying to minimize the function without exploiting any information about the condition, the necessary condition on the derivative. So that's the second class of methods, is if we operate directly or on f of x directly to minimize f, then the process is called the direct method. Now, believe it or not, indirect methods actually came before direct methods. It seems kind of stupid, right? I mean, you think, well, it's indirect, right? You think they would come after, right? Or you think the more direct thing would come first. Well, it turns out that from a mathematical standpoint, indirect methods came first. Now let's go to the optimal control problem. So we can see a little bit about how this relates to optimal control. You remember that in an optimal control problem, the necessary conditions, what we got was we get this Hamiltonian boundary value problem, which has this particular form, where x dot is equal to minus, or is equal to h lambda, and lambda dot was equal to minus hx, right? So we got this Hamiltonian system, and we also had a bunch of boundary conditions. We've got these boundary conditions that phi of x of t0, x of tf, and tf equals 0. And we also have the transversality conditions on the costate. So plus the transversality conditions on the costate. So now let's look at this problem just slightly differently. Let's just reformulate the notation a little bit. I did this once before, but I'm going to do it again. If you say let p equal x and lambda, then the dynamics of this system have the form p dot is equal to g of p, where g is this Hamiltonian vector field, but I'm just going to denote it g, right? Plus, you've got a condition, I'm going to call it psi, which is a function of p, and it's also a function of t0 and tf. So actually, I'd be a little more careful than this. It's not a function of p. It's a function of p at t0, p at tf, or it's t0, p at tf, and tf equals 0. So all we know is we have this dynamical system that needs to be integrated, and we have these boundary conditions that need to be satisfied. So how are we going to solve this problem? Well, let's go back over here for a second, because this is the reason I wrote this down. Notice that this problem over here of finding roots, there's no one way to do it, right? Can you do this problem analytically for a general function? Absolutely not, right? Unless you have some nice structure like you get a quadratic or a polynomial or something where you can easily compute the roots. If I give you like a transcendental function, you can't just easily compute the roots. It's going to be a lot more work to compute the roots, right? So a transcendental equation requires some sort of iteration. Well, the same thing's going on over here. Let's say that I've got these values at the endpoints. And I want to find a set of values such that this function equals 0, and I integrate these dynamics. I'm going to go from one end of the interval to the other such that this thing equals 0. What I've got is I've got a root finding problem. Because there's the equation that needs to be satisfied, and it's a root finding problem, right? So there's nothing fundamentally from a sort of a conceptual level that's different about this problem than that problem over there. The only difference is this is not just an algebraic problem anymore because it has a differential equation in it, right? So it's a differential algebraic problem, so it's more complicated. But in order to solve this problem, you have to have some process that would allow you to be able to do this. So today what I'm going to do for a starting point is I'm going to introduce you to the most basic method that's used to numerically solve an optimal control problem. I did a little bit of it last week with the shooting method. I'm going to be a little bit more formal about it today. It's called the shooting method. And what it comes down to is this, is if I want to find the roots, what we do is we can use Newton's method. All of you familiar with Newton's method? Do you know what Newton's method is? Can you derive Newton's method? If I did it on a qualifying exam and asked you to derive Newton's method, could you do it? Probably not. Oh, that's okay. That's not a big deal. We'll do it now, okay? So in Newton's method, we want to do this. We have a function g of x, and we want to find its roots. So we want x such that g of x is equal to 0. Well, if I just plug in some random value of x, it's not going to equal 0, right? So what we do is we do this by iteration. So we say, suppose we start with an initial guess of x. We call it x0. It's the first iterate, right? And we say that x1 is going to be equal to some x is going to be the initial value plus some delta x0, right? And we do this process over and over again, where x at k plus 1 is equal to the previous iterate plus some perturbation, which I don't know what that perturbation is. But I'll figure it out in just a second. And what we do is, in Newton's method, is we say we're going to try to drive the function closer to 0 from wherever we are. And the condition is this, is to suppose we let g of x plus delta x equal to 0, right? So we say we're just going to assume that we can do this. So if I perturb this function by do a Taylor series expansion on it, what I get is I get g of x plus the partial of g with respect to x. I'm only going to hold first order. And then times delta x is equal to 0. So if you solve this for delta x, you get delta x is going to equal dg dx inverse times g of x. So you can think of it this way. If I'm at the kth iterate, then this is going to equal the partial of g with respect to x evaluated at xk times g of xk. There's a minus sign in here. Sorry. So if I do that, and I put it into my little iteration equation over there, I've got xk plus 1 is equal to xk minus the partial of g with respect to x evaluated at xk times delta xk. Okay? So this gives me a way of being able to update, and then I keep iterating on this until eventually I find a value such that xk plus 1 is equal to xk, and this whole thing winds up disappearing and going to 0. And so I get an equilibrium point for that equation, which is going to be a root of the function. Now, this method is algebraic. It has nothing to do with this problem over here, but you can make it have something to do with this problem, which is, think of it this way, where now I've got these set of parameters which are governing what goes on at the endpoints of my problem. I've got something happening at the initial condition, something happening at the final condition. The initial conditions depend upon the state and the co-state at the initial time, and it also may depend on the initial time. The things happening at the final time depend upon the final state and the final co-state and then the final time. But I don't know what the value is that's going to make this whole thing equal to 0 and going to satisfy these equations at the same time, right? I've got to integrate these differential equations. So what you do is you go through that process over there where this whole thing right here becomes a function generator, because that function g over there is just a function generator. So what you've got is you've got this picture, which is similar to the picture I drew the other day, where typically what you do is you're integrating these dynamics for a bunch of values of p. So you can look at this as being, you can plot p here as a function of t if you want to, and this is t0 and this is tf. And the process of doing this can be done in the same way that you would solve an algebraic root finding problem using Newton's method. You solve this algebraic system together with that differential equation in such a way that when you pick the value here, if what you get when you plug in your unknown conditions into this isn't equal to 0, you then update by saying, all right, well, I've got to integrate the dynamics, and now I'm going to integrate the dynamics, and then I'm going to say, what's the next value of the iterate that I need that's going to drive me closer to this function being 0? And so it's going to give me a new set of values. I'm going to plug those in, and then I'm going to iterate again. And I'm going to keep iterating, and I'm going to use this equation right here. The only difference is my function involves more than just this function psi. It also involves these dynamics, because if I just was looking for this wouldn't be enough, right? Because I need to know how I'm going to get from one endpoint to the other. So every single time I do this, I've got some set of boundary conditions here, and I've got some set of boundary conditions here that need to be met. So if I make a guess, and I say, all right, well, these boundary conditions aren't met, so I'm going to make another guess, and I'm going to keep guessing until I get somewhere such that this thing winds up getting me a little bit closer to these points, till finally I pick a set that gets me such that all the boundary conditions at this end and all the boundary conditions at this end are satisfied, and I do it using that approach right there. Now remember, I told you last week that one of the problems with the shooting method is that these optimal control problems have these issues with stability, right? And we talked about this when we did the linear quadratic problem, where you saw that one of the eigenvalues was in the right half plane and one of the eigenvalues is in the left half plane. So if this interval that I'm integrating over gets very long relative to the rate of change of the dynamics, in other words, the time scales on which the dynamics evolve, this thing's you're going to wind up blowing up if you don't make a good guess at the unknown boundary conditions, right? So what we do in that case is we actually develop a slightly more, if you want to call it, comprehensive way of doing this, because this is what's called indirect shooting. So this method that I'm just putting up here is called indirect shooting, where you solve that problem straight by Newton's method. So if you apply Newton's method to that boundary value problem over there, that's typically what's called indirect shooting. If you want to take the next step and say, well, if the problem is too sensitive on the interval t0 to tf, then the shooting method is modified as follows. What we do is we take this picture and we kind of clutter it up a little bit. We break the problem into a bunch of intervals. And we say that we call this T0, T1, T2, all the way up to Tn minus 1, and then Tn, which is equal to Tf. And what we do is we say, well, we're not going to integrate across the entire interval from T0 to Tf all at once. We're going to break it up so that we're going to integrate over smaller intervals. Now, the problem that people experience with this multiple shooting method is it's kind of a weird thing, because if you look at it the wrong way, it just doesn't make any sense, because you say, well, if I am integrating from T0 to Tf, and now all I'm going to do is I'm going to break this up into smaller intervals, what's the difference between integrating from T0 to Tf and then going from T0 to T1 and then T1 to T2 and T2 to T3, because in the end I'm going to wind up doing the exact same thing. But you're not going to do the exact same thing, because at these interfaces here, you're not just starting off from where you left off at the end of the previous interval. What you're doing is you're going to introduce a new set of parameters at the beginning of every segment. So let's like put these with a circle and a dot so you can see what I'm talking about, which is that these here, all the circles and dots, are values of the unknown state and costate at the beginnings of the intervals. And I don't know what these values are. I'm going to guess them. So what we do is we add, in the multiple shooting, this is called multiple shooting. In the multiple shooting method, we divide the problem into subintervals. And add a new parameter p of ti that corresponds to x of ti and lambda at ti at the start of each subinterval. Now, you can see that if I start here and I integrate to that point right there. Let's suppose we say I'm going to say p tilde of ti be the result obtained by integration of p dot equals g of p on ti minus 1 to ti. So in other words, I'm saying I'm starting at ti minus 1. I'm going to integrate to ti. This value right here, well, it's not labeled with a circle and a dot. Put a square there. This is p tilde of ti. This here is p of ti, which is the new parameter that I've introduced by introducing these new subintervals. What you're going to do is you're going to have these additional conditions then that are going to be augmented to the original problem, which are going to look like this, which is going to be p tilde, I should write it this way, you want p tilde of ti to equal p of ti. So not only do you now have to guess the unknown values at t0 and the unknown values at tf, but you have to guess all of these values as well. So in other words, p of ti, for I going from 1 up to n minus 1, are new parameters in the root finding problem. So in addition to all of those boundary conditions psi that have to equal 0, you now have a bunch of additional conditions that say that p tilde of ti minus p of ti also have to equal 0. And that's for I equals 1 up to n minus 1. Does this make sense to everybody? Or is anyone confused about this? If you're confused about this, please let me know. Yes? Somebody's confused because I've got a bunch of blank stares out here. Who's confused? If you're confused, raise your hand. Or does this all make perfect sense? Yes? No? Are you confused?
A little bit.
Okay. So tell me where you're confused.
What I'm confused about is why can't we just start off from where I teach you that? Why don't we just start off where we stop?
No, that's the whole point. Remember, okay, now that this is what I said. This is the common confusion that comes up in this method. Your question is the one that 99 out of 100 people will ask. Okay, so that's really good that you asked that question. All right. So what the question he asked was, why can't we just start off in this interval where we left off at the end? Right. Remember what I told you is that I said if the problem is too sensitive, if I'm integrating from t0 to tf, suppose I didn't do this. Suppose I went back to this picture over here where I'm just integrating from t0 to tf. If my dynamics have these has this exploding behavior, because remember I showed you last week that the linear problem has a positive eigenvalue and a negative eigenvalue. If I integrate forward in time, that positive eigenvalue, if I integrate for too long a period of time, the problem's going to blow up as I go forward, right? So if I just integrate from t0 to tf and my problem is too sensitive, then what's going to happen? I'm going to blow up, right? So if we do what you suggest, which is that we integrate to ti and then we pick up where we left off and integrate to the next value, we're doing the exact same thing that we were doing over here. So there's no difference between doing this and doing that, right? What this does is it mitigates the sensitivity of the integration, because now what we're doing is we're saying start here, make a guess of this value. I should put a circle and a dot here. So I'm making a guess of whatever the unknown boundary conditions are here. I integrate to the first end of the first interval, right? Make a guess of what I think the value is at the beginning of the first interval and integrate to the end of the second interval. This value is not the same as that value. This value is my guess, right? I make a guess, I integrate to here. And then I do the same thing. I make a guess at the beginning of this interval, and I integrate to here. These values, I'm going to label them all with squares. These values are the results of what I got from the integration by using that value as my guess, right? It's different from the value that I would have guessed. I don't know what to guess here. I'm going to guess something. It's going to be, I could guess all zeros for these values right here. Then what I do is I say, all right, the value that I got from the end of the integration doesn't match the value that I guessed for the beginning of that integration, right? So, but I want them to match, right? So what I'm always going to be doing is I'm going to be integrating over these smaller intervals in such a way that whatever I get from the result of the integration, I'm going to make sure that it matches the value. This is a new variable in my root finder. Each of these are variables in my root finder. So does that make more sense now? So now what you're doing is you're not just picking up from where you left off. You're saying I'm going to integrate over shorter periods of time, and this is what's typically called in root finding, it's called a checkpoint constraint. It says that the constraint is that the value of the integration has to match the value that you're iterating on, right? Until the two values match everywhere at all these nodes, I'm not done, right? This is also what's called parallel shooting. And the reason it's called parallel shooting is because it's called multiple shooting, but the reason it's called parallel shooting is because you can do it this way. It's kind of strange to think that you could do it this way, but you could think of doing all of these integrations at the same time, stacking all of them up one on top of each other. So when I integrate from here to here at the same time, I'm going to make a big function, and I'm going to integrate from here to here and from here to here, and I'm going to keep doing that for each of the intervals. So I don't have to wait for this integration to be done to do this integration. I can do them both at the same time because I'm integrating the same vector field. I'm just integrating with a different starting point, right? Here I'm integrating with a starting point at t0. Here I'm integrating with a starting point at t1. And I can just integrate them all together. So this is also what's called parallel shooting, where I'm going to parallel shoot, and all of these conditions are added to the original boundary conditions as one long vector that the whole thing has to equal 0. And then I'm going to say that whole thing's going to equal 0, and I'm going to iterate on it with Newton's method the same way I would have had I done the standard shooting method. But notice that when I do this, I'm doing the integration over shorter periods of time. So if there's something that's blowing up as I'm integrating in a direction of time, I'm not giving it the opportunity to get very big, right? Because I'm doing it over a shorter period of time. Does that make sense? Right? So these are the two core numerical methods that were originally developed to solve optimal control problems. Because in the early days of optimal control, if you can imagine this, we didn't have all the processing power that we have today. We have very little processing power. And so the reason these methods take on such appeal when you think about sort of historically the way that this was done is you don't introduce a lot of variables into the problem. For example, in the original problem in shooting, how many variables do you have? You have at most 2n times 2, right? You could have 2n unknown initial conditions. Well, you can't, but you could have, in theory, have 2n unknown initial conditions and 2n unknown terminal conditions, right? You have 2n comes from the fact that the state is dimension n, and then the costate is also dimension n. So at most, you could have 2n unknowns at the beginning, right? And at most, you could have 2n unknowns at the end. So let's suppose you were doing a problem that was had a problem which had a state of dimension 6, which would be a typical problem that you would be doing if you were solving like a mechanics problem, right? Because 3 for position, 3 for velocity. So you have six components. So your state is 6-dimensional. Your costate's also 6-dimensional. And then you've got 1 at each end, so you have 24 variables, right? Well, 24 variables isn't a lot of variables, right? It's a very small number of variables. So if you're doing this on a computer that was like an ancient machine from like the 1960s, you probably were at your limit as to how many variables you could actually store in memory because there wasn't a lot of memory available, right? So you couldn't do this large computational process. So then what you would do is you would take those variables and then you'd integrate these differential equations, and the integration would also be done in such a way that every time you took an integration step, you'd throw away the information from before because you couldn't store it in memory, and then you'd start from where you were, and then you'd integrate to the next step, and then you'd throw that away, and you keep doing that, only keeping the things in memory that you absolutely need to in order to be able to do the process. So simple shooting, which is what this is, has a really nice appeal to it when it comes to memory requirements. It's a very low memory process, right? Multiple shooting now adds to that and says, well, I'm going to introduce some more variables in the problem. How many am I going to introduce? Well, I'm going to introduce 2n variables at each of these interfaces. So if I have, say, n segments that I'm integrating over, then I'm going to get 2 little n times big N, where each one introduces a variable at the beginning of the segment. Well, there are a lot more variables in that problem, right? But the constraints that I've added are actually pretty simple constraints. They're like linear constraints, right? So these are not complicated conditions that I'm adding to the problem. So the trade-off is I make the problem more memory intensive, but I mitigate any issues that would occur because of the instability in the Hamiltonian system. So this was the classic way that this was done. Now the problem with both of these methods is that clearly you can see that as these functions get very, very complicated, this is going to be very, very difficult to do when the problem keeps getting bigger and bigger and bigger. So, but for starters, what I think would be really useful for all of you to do is all of you can get access to MATLAB in some way. So I think it's really useful for you to just try solving that linear quadratic problem that I talked about last week, because it's a linear problem. Just try solving it with MATLAB for some small value of TF. Pick a value for A, B, Q, and R. Make them all ones, just to make it easy on yourself. And just try to solve the problem on the computer. It'll probably take you, a few hours the first time to set it up because you don't have much experience with this. And if you have problems with it, come to my office and come talk to me about it so we can go through it. Because you'll learn a lot just in the process of actually having to do it for that simple problem. Because once you can see how to do it for that problem, you can do it for almost any problem because it's all basically the same. It's just that your equations aren't nice and simple. They may be more complicated, but you're doing a root finding. And I think MATLAB has a function which I don't think it's the best function to use for root finding. It's called fsolve, but you could actually set up fsolve to just do this. It will like solve for the roots, and it's a really simple way to get yourself into the numerical aspect of optimal control without getting too complicated. If you try to do this with parallel shooting is a lot more work to set up. You've got to you could try it maybe by 2 segments or 4 segments or something like that, but don't try to do it with like 100 segments or something. That's going to get to be a little unwieldy. But this is a simple way to get yourself into the computational part of optimal control. So I wanted to go through this today because I want everyone to understand that in reality, we just don't have the ability to solve these problems analytically. We can't like construct those kinds of solutions because most of the time our differential equations are nonlinear, and even worse, the boundary conditions can be very, very complicated. And so these techniques are actually used, and this is from a pedagogical standpoint. These 2 methods are sort of the baseline from which all numerical methods are sort of done with optimal control. If you go into, I'm going to go into direct methods later in the class. Direct methods are fundamentally very different from indirect methods, and so that's why I don't want to talk about them today because we really haven't talked enough about optimization, about nonlinear optimization. I need to do that first before we start talking about direct methods. So this is all root finding, so I can stay away from, nonlinear optimization when we do this. So the next thing I want to do today is, so we're done with this. The next thing I want to do today is I want to just start by talking a little bit about, and we're not going to finish this lecture because it's almost 1:30, but I'll start it. And then next lecture, we're going to actually go through an example where we use all this, which is I want to talk about Pontryagin's minimum principle. And so let's go through this in a little bit of detail. So we're going to shift gears. We're going to go back to theory now. Pontryagin minimum principle. If you remember, when I derived the optimality conditions for an optimal control problem, I made the statement that assume that the control had no limits on it. Let's suppose we had a problem where the optimal control was constrained. So if I plot u as a function of t, I've got these limits that the control cannot be in this region, and the control cannot be below this. So it has to stay inside this area here. And let's just suppose that the optimal control looked like this. It hums along, but suddenly it has to take on a value that's at one of its bounds, and it has to go up and maybe ride along its upper bound. So the optimal control, this is u star. You can see that u star of t no longer is free because it's constrained and it's actually hitting one of its upper or its lower limits. This is actually a condition that comes up quite frequently in real problems because, like, if you had a real problem, your actuators have some limits on them, right? They can't just do whatever they feel like doing. You can't change the angle of attack of an aircraft from one value to another value instantaneously, so there's a limit on the rate at which you can actually change the angle of attack. Or you may not be able to change it to the value you want to. You may need a 60-degree angle of attack, but your aircraft can only do 10 degrees, right? That's all it's capable of doing because otherwise it's going to destabilize and it's going to crash into the ground, right? So, and you don't want that. So you've got limits, and you may actually be riding those limits. So the general thing is this: suppose that x star of t and lambda star of t are the optimal state and costate, respectively. Now, we know that the cost functional, if I evaluated it at any value u, let's suppose I'm going to do it this way. I'm going to say u, holding the state and the costate fixed at their optimal values, right? If I plug in any value of u, this is the cost functional of the original optimal control problem. It has to be bigger than or equal to the cost functional when I evaluate it, u of t. At any other control, at the optimal control, and again, holding the state and the costate fixed at their optimal values. So what I'm doing here, this is kind of a backwards argument in some ways, and a lot of people don't like it, but it's the way the minimum principle is formulated, is that I hold everything at its optimal value except for one thing, which is the control. The control is allowed to vary, all right? If it's at its optimal value, the value of the cost functional is going to be smaller than it would be at any other value, right? Because it's the optimal value, so it has to be a minimum, right? So what we do is let's just take that one term in the cost. If you remember in the cost functional, when you take the variation in j, which is now a function of u star, and the variation in u star, right? Because I'm holding everything else fixed at its optimal value. It's going to be equal to, it's going to be such that if I say j evaluated at u, it's going to equal j evaluated at u star plus the variation in j of u star variation in u star. Right, sorry, u star variation in u. Variation in u star. Now, if you look at that, you can actually see that this variation in j, if I evaluate it at u star and then this variation in u, there's a term in this cost that actually comes into play, which is this term right here, which is the partial of h with respect to u times the variation in u, right? That's one of the terms that you're going to get in this equation. But if you look at this term right here, this is going to be evaluated at the optimal control because my variation is being taken relative to the optimal control. Let's look at this term for a second. The partial of h with respect to u evaluated at u star is going to equal times the variation in u. It's this whole thing. It's going to equal what? It's going to equal the Hamiltonian, if I do this whole thing, the Hamiltonian evaluated at the optimal state and the control and the optimal costate, because I'm holding all those things fixed, minus the Hamiltonian evaluated at the optimal state, the optimal control, and again, the optimal costate, if I hold this to first order, right? So all I've done here is that the partial of h with respect to u times the variation u is the difference in the Hamiltonians, where the difference in the Hamiltonians is taken on the difference in the controls because everything else is being fixed at its optimal value, right? So if you look at this, then the first, this term here, which has this, is then going to equal the integral from t0 to tf of h of x star u star, x star u and lambda star minus h of x star, I don't have enough room here. Let me write this a little smaller. H of x star u and lambda star minus h of x star u star and lambda star, this whole thing, dt. So in order for this variation to be positive, we need this thing to be positive, right? Because I just said that the cost function evaluated at any other control other than the optimal control has to be bigger than its value at the optimal control, right? So this has to be bigger than or equal to 0. The only way you can guarantee that this thing's going to be bigger than or equal to 0 is if this is true, that h evaluated at x star u and lambda star has to be bigger than or equal to h evaluated at x star u star and lambda star, right? This condition right here has to be met. This condition is what's called the minimum principle. It's also called Pontryagin's minimum principle. It's actually a more general condition than the condition that dh du has to equal 0. It says that if I hold everything fixed at the optimal value with the exception of the control, it's the only thing I'm allowed to vary. If everything else is fixed at its optimal value, then the optimal control is the one that makes the Hamiltonian as small as possible. This is a very important thing because what it does is it reduces this whole complexity of how do you determine the optimal control to a condition that's simply on the Hamiltonian. It says that if I know everything else is optimal, and this is where the backwards part of this comes in. Clearly, I don't know ahead of time what the optimal state and costate are. But the principle says if I knew the optimal state and costate, then the optimal control is the one that minimizes the Hamiltonian. So what comes out of this is that you can now pick the optimal control to be the one that minimizes the Hamiltonian. So what you do is you say, well, let U be the allowable control set or allowable control space. Then the optimal control at any point in time is equal to the control that minimizes the Hamiltonian. So if you look at the statement You'll notice I wrote something like this at the very beginning of the semester, at the very first lecture when we were talking about function minimization, right? This is the same condition, except for now it's a functional condition, right? It says that for every value in time, if you want to be really technical, put a T everywhere here, because this is a pointwise condition. It says that at any point in time, if I'm given the optimal state and the optimal co-state, the value of the optimal control is the one that makes the Hamiltonian as small as possible. It's not just any value. It's the one that makes this Hamiltonian as small as possible. But that control has to be chosen from the space, the allowable space of controls. I can't just choose it from anything. It has to be chosen from that particular set. So what I'm going to do during the lecture that we'll have at 3 o'clock is I'm going to give you a really good example of where this comes up. We're going to go through it in a lot of detail. It's just going to be that one example. And this is actually a very practical thing, because in applications that actually come up in real problems, this minimum principle actually needs to be applied. It's not just like a made-up mathematical quantity. It's actually something that really it affects real problems. I'm going to give you a model problem that is based on a mechanical system that you'll see that it actually really does make a big difference. And we'll stop this lecture with this right here, and then next lecture at 3 o'clock I'll go through the example. Okay? Right. And now if you have any questions on the shooting method or the multiple shooting method, feel free to come by my office.